Thanks for having me here, and thanks for being at this early morning today. And I thank all the organizers, especially Radhika and Suraj. And also, perhaps you might have expected Kasra to be here because, yeah. So I'm a friend of Kasra, and Kasra asked me if I'm interested in visiting India. So he recommended me to come here. So it's a great honor to be here. So yeah. So today I'm going to talk about growth of groups. Today mostly groups with some hyperbolicity. So as the course proceeds, I'll move on to some more groups in more generality and also some subgroups. But today probably I might gonna talk about only hyperbolic groups. So yeah, let's go slowly. But I want to first begin with some motivating examples. And also some setup. So throughout, X is a metric space, but in order to make sense of the growth problem, when there's some control on the geometry. So it's a proper and geodesic metric space. What does it mean? So it's a metric space, like Euclidean space or hyperbolic plane or hyperbolic 3 space or so on, which is satisfying two properties. First, the properness means it's a metric space, so you can draw a ball of radius r. So if you draw a ball, closed ball of radius r, it's always compact. So that's what I mean by properness. Geodesic, so this is compact. The geodesicity means if you're given 2 points, you can always take the shortest path. So you can connect each pair of points with the geodesy. It may not be unique, but yeah. And probably it's convenient to fix a base point, x naught. And then G is a countable group acting on X properly by isometries. So X is a metric space, so you can think of isometries. We're going to take a countable isometric group of X, but we also want it to be compatible with the this controlling the geometry of X. So what do I mean by proper action? In this context, since this is countable, it basically means in any finite radius, you only have finitely many orbit points. So there's no infinitely many ones accumulating inside a finite radius ball. Okay. A motivating example is the hyperbolic plane with an action by a Fuchsian group. So this is just a discrete group action on H2. Then it will give rise to a surface, hyperbolic surface. So here, this is one fixed ingredient, hyperbolic plane, and this is one category of groups, but you will get tons of variety of resulting spaces, such as closed surfaces, or you might also get some cusp surfaces, or you might have some funnels. So this kind of things also arise. Of course, if you do not impose any further restriction on G, you can get a totally bizarre surfaces like so. infinite genus, infinite like endpoint, like infinite end space, but yeah, mostly we'll focus on these kind of categories, but yeah, I'm just telling you, this is already quite general setting, like giving you plenty of like objects. And also it fits well with low dimensional topology and like geometric group theory. So if you study the hyperbolic surfaces as a resultant of the group action of H2, what can you ask? What kind of objects are you interested in? So one fundamental object is the submanifolds, or in this case, curves. So people have been interested in what kind of curves you can draw on the surface. It could be like this. It could be slightly more complicated than this, like so. It's slightly longer. You can also draw something like this. And if you do not require them to be closed, then you can even draw something like very crazy things like this. So our question is, how do we understand the family of the collection of curves in surface? There's no concrete answer to this question because like you can ask your favorite questions about curves. So I'll just describe some facts that I know, and probably that's gonna be the starting point of this lecture. So first, so all curves drawn here can be drawn by, can be obtained by drawing one curve here, and then you project it down here. Why do I do that? Here, all geodesics or all curves have some, you have some more uniform understanding of those geodesics here. Basically, there's only virtually one type of geodesic. You just draw it, and then how it appears in the downstairs, it really depends on the group action. So that's how we understand, that's one way to understand the shape of curves here. So if I pick, so how do I actually draw geodesic here? You just pick a base point. It could be arbitrary. You pick a direction. That already determines you. That already gives you a geodesic. So you can ask, depending on the choice of unit vectors drawn H2, what kind of curve do you get here? So one fact is, if you draw geodesic upstairs, then most likely geodesic gamma on will most likely not close up downstairs, but will almost close up. What do I mean by this? Let's try it 1 second. So there's a chance that your choice of geodesic might close up like this. But this is quite fortunate situation. You were very lucky. And the collection of such vectors are, like, in some sense bigger compared to the entire set of like vectors that you can choose. So what's the generic picture? The generic picture will be, you will go very randomly everywhere. You might stay in some subsurface, but that's also very unlikely. So you will travel all around here. Sometimes, and like infinitely often, it will come closer to the beginning, the departure point. But there, the direction will not match up exactly. But if you wait like sufficiently long time, it will match up sufficiently close to your initial direction. That's what I mean by it closes up almost, like it almost closes up, but it doesn't exactly close up. So this is a generic picture. Yeah. However, still you might want to study this set of closed geodesics because they are nice. If you want to do that, actually this kind of fact helps when you study closed geodesics, especially the fact that it will almost close up. I will elaborate on this fact later on. But the second thing is, if you get our closed geodesics in sigma correspond to conjugacy classes in pi 1. So if you want to just emulate one closed geodesic, you just make a non-trivial loop at a base point. But actually, the base point should not have a relationship to the innocent like closed geodesic. So you should forget it. So how do you forget it? You just take the conjugacy class. And third fact is closed geodesics are in some sense ubiquitous downstairs. So I should say the union of closed geodesics is dense. This could follow from the first fact that like whatever like geodesic, not necessarily closed geodesic, you draw on surface, most likely it will close up. So if you want to hit one point, then you just draw just arbitrary, just random geodesic starting at that, and then you will most likely be able to close it up like without perturbing the initial like vector that much. So that's how you prove it. Sorry? Oh, a dense, sorry, in sigma. Thanks. Mm-hmm. Mm-hmm.
I can see how you maybe perturb the initial vector to make it actually close up.
Yep.
But I don't see that would close up smoothly. Right? So can you make it close up smoothly? Like, is that a thing? Or?
So yeah, there's some subtlety, more precisely. So if you have one geodesic, and then so this is upstairs, so you have another like copy of this one, like translated of your beginning point here, and then it came really close, and your beginning like direction is almost like very nearby, but it's not exactly the same. Then how do you do that? You cannot close it up by just changing the direction here. You should also slightly change the base point as well. then you can smoothly close it off. So for example, I can phrase this like almost like there's a dense subset of like unit tangent vector, unit tangent bundle of H2 that will give you a the closing of directions, but they're only dense, so they're not, for example, almost sure, like almost every directions in some sense, but still. Okay, and I should make a caution because I'm deliberately choosing this word because sometimes closed curves mean simple closed curves in low-dimensional topology, but I'm not meaning that. Because, for example, simple closed curves correspond to some conjugacy classes in pi 1 sigma, but they're not all like conjugacy classes. And also, the union of simple closed curves will not be a dense subset in sigma. That's a bit non-trivial like fact, but that is true. Actually, it's quite meager in some like topological sense as well as measure theoretic sense, the union of simple closed curves. So I'm really meaning simple closed geodesics, or not necessarily simple closed curves, like as opposed to simple closed curves. Okay, these are facts, but the fourth item is really not a fact, but this is like a perspective. This could sound like a metaphor, but it will be made more precise later on. So there's a finite room or finite stage that you have, but unbounded quantity or unbounded length. And here I will say finite volume. So here, like if I'm sticking to this kind of like compact surfaces or in general finite type surfaces, but let's stick to compact surfaces, it has finite volume, but a priori there's no like bound on the length of closed geodesics, right? So how can you make arbitrarily long closed geodesics in this like finite volume room? It should get convoluted, right? It should go around several places multiple times. Like the shape will go like absolutely crazy, and also there are infinitely many like such closed geodesics. So it's quite like out of control, like at once. So if you want to systematically study closed geodesics, there should be some way to reduce it to some finite estimates, and then you just see how it evolves when you increase the threshold. So this is not a fact, but this is rather perspective that guides you to the dynamics that you should study when you're interested in curves. So this gives us perspective that, so our philosophy is there are too many closed geodesics, so I take finitely many closed geodesics, and see how they evolve. So see the asymptotics. So which kind of asymptotics are you asking? That really depends on your flavor, but in order to answer this kind of question, you should do some kind, like you should construct some kind of dynamical system and like examine its property. So that is the question that I'm interested in. So this is the end of motivations. Now I will phrase a question. So sigma be, for now, compact hyperbolic space, hyperbolic surface. Then what is the asymptotics of the number of closed geodesics on sigma with length smaller than L as L increases. This is probably the simplest or the beginning question when you take this kind of perspective. You should, like, you can ask further questions. For example, as I told you, like curves with like longer length should be more convoluted. So how convoluted? And are they hitting each place in the surface in an equal or fair sense? So do they equidistribute? If they equidistribute, what's the limiting object that you get at the end? Or something like that. You can ask all these questions. But before asking all these things, this is probably the most simple-minded question. And this is now a classic, because it has been answered by many authors multiple times in different generality. Oh, I see. Oh, yeah, sure. So I should give you precise definition. So let's say this is a quantity that's determined by the threshold L. So this is a function of L. So IA is you can ask something like, is FL polynomial or exponential? Or more better, can you find a simple, how do I say this? Like exponential function, like polynomial function, or like combinations of those such that their limit tends to 1 or some well-known non-GL? This is the question I'm asking. And this was answered by Heinz Huber, in 1952. So it's been studied for a while, right? He showed that FL is in the order of exponential function divided by a linear factor. That means FL is comparable to this function, i.e., if you take the limit of FL, the ratio between FL and this function, this is 1. And Margulis famously proved this in more generality in his PhD thesis, that in general, so basically there's no special point about dimension 2 for this question. For compact manifold with the sectional curvature bounded by from below and from above by two negative reals, FL. So if you're given this compact manifold, you do the same. You ask the same question: what's the asymptotics of closed geodesics, the number of closed geodesics drawn on that manifold? Then this is comparable to e to the sum. So it's comparable to this function for some h. And for dynamicists, this quantity h is quite important. So just to summarize, I will not go into details, but for example, this is called the volume entropy of the universal cover of this compact manifold. This is important quantity to look at if you want to prove some volume rigidity of the manifolds, such as among all the like compact manifolds that you can draw, like among all the differential geometric like structures that you can put on that manifold, what's the most optimal like structure that you can give? It's got to be a symmetric metric, like it's got to be coming from the symmetric space. How do you prove it? Like you try to optimize, like lower down this quantity depending on this structure of manifold. But that's not that important to us. It's just that there's a positive constant that can be read off from the geometry of compact manifold such that you can determine the asymptotics. So in some sense, yes, H sometimes depends on B and A only. So what do you mean by that? If you require B and A to match, then it's just hyperbolic metric or just a dilated versions of like hypermetric. Then it can be read off. I mean, there's only one like metric structure that you can put. Then that's H is read off from that constant. So that's why you get a like here H is 1, and this 1 can be read off from the constant like negative curvature of hyperbolic plane. In general, this kind of negatively pinched curved manifold setting, it really depends on the geometry. So how large portion of the manifold is more curved, whereas how large portion is relative not curved. Like it really depends on every aspect. But it can be determined from the geometry. And these are the classics, and I can go on some more like list of references. This is Hoblang answered this for Chem -1 manifolds, and his point was to make this statement for geometrically finite manifolds, which means in this case, Margulis answered this for compact manifolds, but if you allow some cusps, like some well-tamed like cusps, then can you do the same game? Yeah, you can do it. And also, if you move out from negatively pinched curve like setting, but non-positively curved setting. So how about K0 manifolds? Nieper also answered to this setting in some sense. And finally, I'll add one more reference. Askin and Mirzakhani. Oh, sorry, rank 1. Sorry. This is rank. I used hyphen, but yeah, like rank 1. Yeah. I will elaborate on later, perhaps. Yeah. Sorry. Yeah. I mean, this is just to give like due credits, but we'll soon come back to our home, which is hyperbolic plane and hyperbolic surfaces. So please bear with me. Finally, they answered this question for Technion space. I will not define Technion space right now, but still, I'll just give the credit. So, and it's questioned by mathematics group, which is the moduli space of curves. Yeah. Okay, so it has been answered for like various spaces with varying amount of hyperbolicity. But let's try to prove it ourselves. So okay, I will keep it. I'll write more there. So today's goal for the remaining time is sorry? It's yeah, closed geodesics in moduli space, I should say. Yeah. Thank you. Yeah. Acronym space does not have like closed geodesics. Yeah, that's true. So yeah, this is really regarding moduli space. Yeah. So today, let's prove it for, let's say, pi1 sigma. Force action on a hyperbolic plane, or even its Cayley graph, or any properly discontinuous like compact actions on a delta hyperbolic space. That's our goal. But before going to proof, I will add some more words on like previous approaches. Huber did obtain this kind of asymptotics by some very analytic like method. So it really mattered that H2 is really a bunch of matrices. Like H2 is actually PSL2R quotient by SO2 or something, right? So there you can really calculate some integrals over some matrices so that you can obtain some like zeta functions or something like that. So the method was quite analytic, like calculating all the integrals. Margulis' approach to this problem in a different way. He really did some dynamics. So he built up some dynamical transformation. He constructed he extracted some like measure space from H2 and its boundary, constructed measures, constructed limits of measures, and from the existence of certain limiting measure, the asymptotic followed. So it's quite mysterious. It sounds quite mysterious, but it's really beautiful like work. But today I decided to opt out from any of these approaches because I'm not dynamicist. I don't know dynamics that much. So we will go very low key. It will be very geometric and combinatorial. So it will belong to, now, we will prove this via some combinatorial approach. That is due to Kuhnert and Nieper. So I will list some steps for this question. In general, let X be a delta hyperbolic space. So it's the same, like the original setup is brought, remains as is, but I'm just requiring further that it's a delta hyperbolic space. So G is properly acting on the space and co-compactly. And finally, let's add one condition. The action is non-elementary, which means I'm not bringing like real line as hyperbolic space. Like it's really not like you head into independent directions of the hyperbolic space. That's my assumption. Then first step is to prove that this quantity exists. Basically, if you gather orbit points on the universal cover, which is X, that is within the radius R ball, then it should grow exponentially. That is our belief. So how do we make this precise? You take the log, then it should grow linearly with respect to R, so you divide by R. This exists. This is the first statement. And in the course of the proof, you will see that this quantity really does not depend on my choice of x0, the base point. Second, this basically tells you that, so, i.e., this function, this cardinality function, is bounded by, I will use different functions, fr times e to the hr and f prime r, such that f prime r and fr are well controlled. Like, it's not saying that fr and f prime r are both like bounded or something, but it's just saying that the log of fr is sublinear or something. The first statement is really telling that, but the second statement will actually claim that fr and f prime r can be taken bounded. So actually this cardinality function is really comparable to e to the hr. So I will write like this. There exist k1 and k2 such that this is greater than k1 times e to the hr and bounded by k2 times e to the hr. So the second item is more precise information than the first one. Finally, so in this generality for actions on hyperbolic space, the curves, the closed geodesics corresponds to congested classes of the group. So I collect all the congested classes. That is represented by group elements within finite radius. And I count the cardinality. This is really comparative to over R. So these three steps are our goal for the remaining time. Thanks for asking. This will depend on x0. That is true. So it's really important that K1 and K2 might depend on x0, but H, this really depends on, is really determined by the action itself, not on the choice of base point. Yeah. Are there any other questions? Yep. So some remark. This is our day one. So probably this is sufficient for today. Later on, I will give reasons why this holds in much more generality. Remark. This is also true for zero space. Co-compact actions on zero space. So here's this need not be manifold. So it can be just arbitrary K0, like for example, K0 Q complex or something. This is due to Gechtmann and Yang. And also the same strategy, although it has been proven earlier by Eskin and Mirzani, Gechtmann and Yang method also applies for the mapping class group action on Teichmann space, which is not co-compact. So they recovered Eskin and Mirzahani's result. And also for finite type hyperbolic surfaces, which may have several like cusps, this still holds, and it has been studied by many authors, but Gekman-Yang's strategy also works for that case as well. So it can admit some cusps. But why am I saying hyperbolic surfaces instead of Kleinian groups acting on hyperbolic n space? If the dimension gets higher, you should pay extra care. So I cannot claim for general like negatively pinch curved manifolds, which are geometrically finite, because geometrically finite like hyperbolic n manifolds can behave quite differently from hyperbolic surfaces. So one should be careful, but at least for hyperbolic surfaces, it really applies to arbitrary finite type surfaces. And I will add some more words. So what do I mean by some like good behavior of hyperbolic surfaces, like as opposed to hyperbolic n manifolds? If you have a cusp, you can associate some excursions to the cusp. So a closed curve might close up in the compact part. It's not compact core, sorry. Like thick part of the surface, it might close up here, but it can go deep excursion into cusp and then come back and then close up. This kind of curves also arise in like cusp hyperbolic surfaces and also hyperbolic manifolds. So, and these are considered a bit bad or like ill-controlled. So in this study, it's quite essential to suppress the population of such curves. And for hyperbolic surfaces, the curves enjoying deep excursions into cusp is population-wise negligible compared to the curves drawn in like nearby the thick part. So that's because basically you cannot have tons of growth by parabolic elements or in the cuspidal part only. But in hyperbolic n manifold, a cusp can have like the peripheral subgroup can be z to the n as opposed to z. And also depending on the relative curvature that you impose on the cuspidal region, like if it's negative, like if it's only pinch negative curvature, the curvature can vary. So you can adjust the growth made by this abelian peripheral subgroup. And in some weird examples, it might exceed the growth rate made by the thick part. And that is the problematic situation that we want to avoid. But for finite type hypersurfaces, that kind of pathology does not arise, so we can claim. Yeah. So open question will be, as far as I know, is this true for non-positively curved and let's say geometrically finite groups? This I have no idea. But there are some like yeah, it could be answered or it could not be answered, but yeah. For Ken-1 geometrically finite groups, it's answered by Rob Lang, but this generality is widely open. Okay. So let's dive into each step of the theorem. one advantage or disadvantage of this combinatorial approach, like as opposed to dynamical approach, is that I haven't mentioned any boundary structure of X, right? So I'm sticking to the delta hyperbolic space right now, so I can definitely employ visual boundary or ground boundary. But in growing generality, like for Technion space or for Ket0 spaces, what kind of boundaries are you looking at? Like if you want to describe the limiting behavior by the dynamical transformation, then sometimes you have to employ the boundary structure. But since today we'll only stick to combinatorial approach, I don't need boundary structure, so I will not describe it. So first step. So why does H exist? And if so, why H is greater than 0? This is much easier to answer because since I'm assuming non-elementariness of the action, I have two independent loxodromics. So this is by ping-pong argument. What does it mean? The assumption tells you that there's a two element in the group that acts like loxodromics on the hyperbolic plane, whose sink and source points are disjoint. In this case, if you take suitable powers of such elements, so by the assumption, there exist independent loxodromics P and P in G. And there exists n such that that's suitably large, such that the orbit map, like from the free group generated by the phi to the n, and this is also phi, but like phi to the n, orbit map. So if you pick an isometry, then you send it to the corresponding orbit point is QI embedding. In particular, it's injective. Hence, inside the ball of radius r, so I will use this notation. This will denote the group elements. It could be confusing, but yeah. Like so. As this is at least 2 to the r divided by the step length. So hence it's exponentially growing, so h cannot be 0. So h should be strictly positive. But this is just a summary. So what's really going on? The correct picture is so on the space, you chose two independent loxodromics that's progressing deep toward its sink sufficiently long enough. And then you make another, so let's say you have phi to the n, and then here you can go further by phi to the n, or by, this is unfortunate, this is also phi to the n, but still. Yeah, you can go either this way or along another transmitted of phi, like phi to the n. And I want to show that all these orbit points are distinct, at least. Actually, it's a QI embedding, but let's first show its injectivity, that the orbit points are distinct. How do you show that? These are not the same progress. How do you know? Because there's a non-trivial angle and there's a non-trivial progress. So it's like an obtuse triangle you draw on hyperbolic space. And then there's another triangle that you see at the next step and the next step. So the question is, if you have this kind of progress on the hyperbolic space where you diverge at each vertex at some relatively early stage, and then you make sufficient progress that's given by the power, like the powering up, then can you show that this edge is non-trivial? So in other words, can you make this kind of round turn? So if it's in Euclidean plane, whatever obtuse angle you impose for the vertex angle, for sufficiently, if you take sufficiently large like step, you can come back to your original place, right? But in hyperbolic plane or hyperbolic delta hyperbolic space in general, it can never happen. Why is this the case? For Chem-1 space, it's rather easier to observe. So we want to make an induction that, okay, this angle is obtuse, that I can guarantee. And then this side length is sufficiently large, that also I can guarantee. I want to inductively prove that the angle made by nth progress and the next step is still obtuse. Let's see. How can I make it? So let's say I prove this angle is obtuse. It means my initial point is lying in a shadow. What's the shadow? You make the perpendicular arc here, and then you just take the half space. Like in the hyperbolic plane, it will look like this. Then, I mean, compared to the original side that you have, there is a non-trivial change in the angle. That is true. But that change is bounded by, determined by the length of the length of side at step n, not depending on how deep it is here. Okay. So for example, if you can't guarantee that at each vertex you make like 120 degrees angle, and then you can guarantee the length of side that makes this smaller than, let's say, 10 degrees, then you can always win. You can proceed. But in Euclidean plane, you cannot do this. This is the difference. This is where the hyperbolicity comes in. Of course, like this is too geometric. This is an intuition for hyperbolic plane. For delta hyperbolic space, you have different arguments, but basically the philosophy is the same. Sorry. Yeah. In some sense, but like it's in the same line, but it's really regarding finite, like orbit points obtained at finite steps. So this could be, you can do it forever, but this is also applying to finite step as well by induction. So what I'm telling is you have orbit point here, and also orbit point here, here. All are distinct. That's what I want to show. This is the injectivity that we need for this map. So you make a word, like from the free group of rank 2, and then you assign an orbit point, and you should show that they are within a bounded distance that you target. Okay, that's given by the triangular inequality, because you can make bounded step by either of those two isometries, but you should also show the injectivity to guarantee the lower bound of the population. That's what I'm doing here. Yeah, so this is related to that. Like, that is true. So I can phrase it. Actually, I intended to do that next time, but as Zach mentioned, this is really one instant of local to global property. So how do I phrase it? So lemma I draw some consecutive sequence of consecutive geodesics, gamma 1, gamma 2, gamma 3, gamma 4, and something like that. And if the length of each gamma I is greater than, so let k be a positive number, and let's say the length is greater than 2k plus 100 delta, and the Gromov product made by two consecutive geodesics, that's basically how obtuse the angle is between those like two triangles. I haven't defined it, but let's say the Gromov product between gamma I and gamma I plus 1 is smaller than k. So suppose that you have control on how long those two geodesics are fellow traveling, beginning from the vertex, like at each vertex, and guarantee that the length, they are separated well enough. Then what I got is, let's say, sorry for sloppy notation. Then what I get is the ground product between x0, x4, based at xi. So if I measure the angle between x0 and x4 from the perspective of xi in the middle, this is bounded by, let's say, k plus ground delta. So in plain language, if you can require that like the consecutive triangles are all obtuse and the length of sides are sufficiently long, like longer than the threshold that you put for the angles, then you can have the global like obtuseness of the angle. So this is delta hyperbolicity, like the version of this kind of angle argument in delta hyperbolic space. Okay. That is true. So here, Gromov product is x and z based at y. So you have x and y, sorry, x and z, and from the perspective of y, from the viewpoint of y, you want to kind of conceptualize the angle. So how do you do that? This is dxy plus dyz. And you take the surplus minus dx. So if they are collinear, then they should be 0. If x and z are like aligned along a half line, then this could be terribly large. And most of the times it's in between those two extremes. So what I'm telling is, if this quantity is uniformly bounded, and if the length of each side is greater than, like slightly greater than that uniform bound, then you can achieve this local to global property. No, sorry. This is for general n. So yeah, this is like n for okay, so this is how we do ping pong lemma, ping pong argument on Gromov hyperspace. Now the remaining part of step 1 is, does the limit exist? So that really shows that the cardinality function grows at least exponentially. So if you take the limit, if there's limit, if any, that should be positive. So does this really converge to a limit, or does this oscillate? But this is not hard to see. So there's a lemma by Fekete. For any non-negative subadditive sequence of reals, AN, i.e. the entry at n plus m step is bounded by the sum of the corresponding summons, then the limit exists. The growth, like the sort of like growth rate exists. And this is equal to the lim inf of AN. How do you show this? Basically, you show that if you have the steps that realizes this lim inf, that approximates the lim inf, then the entries later than those like approximates should be like closer to that like quantity, sort of like that. Yeah. That can be achieved from the subadditivity. So this is a simple lemma. Why does it apply to our setting? So since now we call the action of G on X is co-compact for now, let M be the diameter of the quotient. So if you think about the case of hyperbolic surface and the hyperbolic plane, then this is just the diameter of the hyperbolic surface. So what do? Upstairs on X, or which is H2, if you prefer, if I have some orbit point here at let's say distance n plus m, you want to chop it down, chop the progress down to a progress in the order of n and progress in the order of m. How can you do that? You draw a geodesic. You see a geodesic downstairs. And let's pick one point P at distance n. Then you begin from x0, and then in the course of the geodesic, the P downstairs might be different from x0, but they are not that too different. Why? Because the diameter is bounded. So there should be some translate of x0 by the group element that's m close to the geodesic, right? So this basically, like, in other words, if you take the m ball of orbit points, then that's covering the entire space. So wherever P is, it's m near to a orbit point. This way, you can show that for each G in the ball of radius n plus m, there should be some surplus, some room of error. So let's say 2m. There exists an H whose orbit point is not that far from geodesic, and that was the resulting estimate. That's and also H prime, which is H inverse times G. which is in this bool, H prime is in small m plus large m, such that G is H prime. So the population of this bool is smaller than, I'll just erase it, sorry. This is smaller than the population at n plus m times m plus n. Hence, if you take the log, this is subadditive. So this, if you define this term, the cardinality at radius n plus m as the nth entry of the sequence, then it's subadditive. So we can apply the effective lemma. Apply the lemma. The limit of the log of cardinality at this limit exists, and this is equal to the growth rate, the h that I defined. Okay. Considering the time, I will finish till step 2, and probably I will resume in the next lecture. But step 2 is not that far from here. So what was step 2? So step 1 is just barely telling us that it's growing exponentially. So there's a exponential function, and the ratio between the actual cardinality function and the exponential function is growing sub-exponentially. That's what we proved as of now. But we want to nail down the error into bounded amount, bounded ratio. So second, so the cardinality function, which now I denote by this, is really compared to e to the hr. The lower bound, sorry. The lower bound is already there. So we should show that there exists a constant such that this is greater than or equal to C1 times e to the hr. Well, but here, the factor lemma tells us that that's actually lim inf, right? So, and I should have told you that this is actually inf. Sorry. This is lim inf, and actually it is also inf. So it is not decreasing, but if you take the infinite, that's the limit. So by factor test lemma, we now have this one divided by n. This is bounded from below by h, and bn plus 2m is honestly greater than this one. So this is greater than e to the h n minus 2m, which I can rewrite as e to the minus 2hm. So depending on the diameter of the quotient, you can get this C1. But the upper bound, we should observe something. So what is the idea for the upper bound? Should I stop here? Oh, I see. Okay, then from next time, I will resume from the upper bound of the cardinal. Okay, then I'll just take 3 minutes. Okay. Yeah. So the idea for upper bound. So what's the idea? So if I have too much population inside a ball radius r, then I want to show that the large population persists if I go further and further. So what I mean is, if I have population BR at radius r, and if I draw this ball radius 3r, now I want to say something like, this is actually the multiplication of BR for 3 times orally, or almost equivalent. In that case, if I have this cardinality like over the desired limit, then it's multiplied again and again, and the limit will actually see that surplus, which is the contradiction. So if this happens, then this implies that this is bounded by actually without a constant, without even a multiplicative constant, we can conclude this. So, but in general, this is not always the case, if you think about it. So there should be some error. So what's the idea? So I will explain it later in the next lecture. If I pick one element from ball radius r, and if I pick another radius, another element and another element, 3 independent elements, I want to assign them an element in ball radius 3r and make this assignment injective. So always, I want to make the contradiction. So actually, contradiction follows from this. So I want to make the lower bound of the ball of radius like k times r. So in that way, I should have an injective assignment from the sequence of elements chosen from BR that has into the ball of radius kr. So that assignment I will resume next time. Yeah. I'll stop here. Hmm? The upper bound will depend on x0. Like you'll see later on. But yeah. Hmm? Yeah. Linear progress? What do you mean? The second item you mean? Yeah. We also have that like results as well in all of these cases. Yeah. That's a great question. I deliberately didn't touch upon that part. But we will see from this combinatorial approach that what we really need is local to global property of among the geodesics. What do I mean by that? If I have geodesics that are consecutively pairwise like well aligned, so they are not going back to like the previous step, so they are progressing further and further like stepwise, then it's making global like progress, so it's not returning at the end. So if it can prove that, if it can guarantee that, then we can get a similar estimate like this. So in Cat0 space, there's a flat. So in the flat, if you make the steps inside the flat, then you can definitely like return back to your original place while making local progresses. So you cannot have local to global property. But if you can plug in rank 1 progresses, so progresses like through geodesics that are rank 1, then the alignment among rank 1 geodesics can guarantee this local to global property. So the key point is consider space to have a rank 1 like rank 1 isometry. Like or ideally like 2 independent rank 1 isometries, but that's often not hard to achieve considering that, let's say like Kapra-Sagi's like rank rigidity theorem and so on.
Any more question? So if not, so let us thank him again.